Okay, so we start with the Condor overview. So I know that some of you, like Todd, will find it boring, but I hope I give enough overviews for those of you who are not Condor experts to make it worthwhile. And just to give all the record that's needed, this is heavily based from what Todd presented last year at CERN. So let's start with what is Condor. So for those of you who don't know it, Condor is a workload management system, which means a batch system essentially. And its strong points are it's fault tolerant, it has a robust feature set, it's flexible, and it has a dedicated team that's working closely with the scientific community. And this is why they're here. They really care about us. So Condor can be used for different purposes. It can be used for managing local processes. It can be used for managing local clusters. It can be used to connect different clusters of local resources. It can handle resource overlays, which is glidines. It can be used for accessing any other batch system, which is essentially Condor G. And this includes classical grids, as we usually call them, cloud, or even just other batch systems like PBS, LSF, and so on. You can use Condor to submit to PBS. So we'll talk about vanilla in this talk, and let's start with the principles. In Condor, there are two parts of the equations. You have jobs, and you have machines or resources. They are pretty much equivalent from the Condor point of view. And the jobs are the Condor's quantum of work. They are like a Unix process. They can fork afterwards, but you start with the process. And they can be further grouped together in workflows. On the other side, the machines represent available resources. Condor is geared really in optimizing the use of CPU, but they also indirectly manage memory and disk. Now, jobs have their wants and needs. Jobs will state in the requirements in their description, the requirements in the preferences, and requirements can be, I require Linux on an x86 platform. Give me another type of resources, I will fail. So don't even try. But I may also have just preferences. Like, I prefer machines owned by CMS, but if you give me something else, I will still use it. The jobs describe themselves via attributes. There are several standard attributes that are defined by Condor, like I'm owned by Albert, like my owner is Albert. And there can be any other custom attributes that the user can add, like I'm Monte Carlo job, I will be done within 12 hours. It's not standardized in Condor. Users can essentially add whatever they want. It's good that there is some consistency, but from the Condor point of view, it doesn't really matter. Any string will do it. And machines have similar properties. They have requirements and preferences. For example, they will put a requirement that I require a job that has declared that will run less than 18 hours. Don't even try to give me something else, I will not accept it. I know that within, for example, 18 hours I have to go away, so there is no point in taking a job that will run longer than that. But they may have preferences too. Again, I prefer Monte Carlo job, but if really you cannot give me anything else, I'll take it. And like with the jobs, machines have attributes, and there are a lot of them that are standard with Condor, like I'm a Linux node, I control 2 gigabytes of memory, but they can be custom that are specified by the machine administrators. And for example, I have been paid with CMS money. That's just an attribute. Of course, it will not be that verbose, but something that means that it can be defined. Now, Condor essentially has a central manager that brings jobs and machines together, like in the classified section of a newspaper. I hope everybody here is old enough that it knows what classified is, because probably the really young kids have never seen it. So how it works, like in the classifieds, you have somebody is looking for something, somebody is offering something, and Condor just brings them together.
Oh, you mean Craigslist?
Yeah. Well, Craigslist is going off the table label too, so I don't know what is the modern equivalent. Jessica, you know what the... It's still Craigslist? I gave up on Craigslist, it's just spam nowadays.
So it's sort of class app language, it should be Craigslist language.
Yes. So what are Condor class sets? Class sets, it's a language for objects, both for jobs and machines, to express attributes about themselves and express what they require or desire in a match. Like we say, we have requirements and preferences. And they have structure. Although the structure is very simple, it's essentially a set of name-value pairs, and the values can be literals, like strings, bools, integers, floats, or an expression that references other attributes in the class set. So it's very rich in the end, although it's simple key-value pair. And with the new class sets that are coming in right now, you could even have trees, if I understand correctly, but I will not go into it. So here is an example. This is what the class set looks like. And here you have a couple attributes that declare what I am. I am a machine, I am looking for a job. This is my name. These are my requirements. I want the job to declare that it is not ITB. If it's ITB, I don't want to care about it. And I don't care about rank, just a number. And there are plenty other attributes that come standard. So, as I said, in the class, values can have expressions. And the expressions look a C-like syntax. They have operators, references, functions. You have all the standard attributes you would expect in a C-like language, plus a type checking operations, which essentially will make sure that not only the value is the same, but the type is actually the same. The others will try to do type checks, type conversions. This will not. And this is also guaranteed to be true or false, while if you try to do equal between two things that don't make sense, the answer would be unknown. You have functions, plenty of them. You can reference other attributes. So if you just put another attribute like it was before, job is ITB, it will look up it and use it. And a few nice things is that true is equal 1 and false is equal 0. That's guaranteed. So you can do something like this and still get a reasonable expression out of it. And they have an explicit undefined behavior. So you can actually say something equal question mark equal undefined, and you can actually look for undefineds. Pretty nice. And here is a link if you want more details. That's really just very high overview. And here you have an example expression that we actually use. And you see you have a function. We actually look for undefined. We do a math, referencing other things. And yeah, you can do ands. So we are mixing logical and numerical values. And I will not go into detail, but just so you see that expression can actually be complicated. And unfortunately, cannot be this nicely formatted. They have to be in a line most of the time. Well, not really. You can do backslashes in the config file, but if you do Condor status, you will see it in a line. So it may be difficult to read, but still. So now you have a bunch of class sets, and now you want to match them somehow. So you have different types of class sets. You have job class sets, you have machine class sets, but there can be other class sets as well that can be either used by other Condor daemons or by other non-Condor processes. So for example, the glideinWMS defines a few of them, and we will see that in the slots later on what they are. So all the jobs, all the machines, as we said, go all together in the central manager, and the central manager is what actually defines what a Condor pool is. So this alone and this alone are just machines. Put the central manager and you get the Condor pool. So after you get everything together, the central manager will do its magic and find a machine for a job. Tell the Condor on the submit machine where this machine is. At this point, it will talk to the Condor on the machine, and the job will start. This is at 100,000 feet what happens in Condor. Now, how this magic of matchmaking works. So, a match is made when two ads match each other requirements. So it's two-way. So job must match, job requirements must match the machine, and a machine requirements must match the job. Only when both of them match each other will a match be made. And if there are many different matches that are possible, the ranks are considered. And the highest rank will win. By the way, which rank will win, Todd? The jobs or the machines?
Which what?
Rank.
Machines.
So, a few more details. We said we have attributes in both sides, and it can happen that the two class sets have attributes with the same name. So, in order to disambiguate which one you are referring to in an expression, you can use my to reference to your own internal class sets and target for anything that is compared against. And if you don't specify anything, first it goes name and then it goes target. So a classic example from the Condor slides. You have a pet ad, which would represent approximately a machine, and you have buyer ad, which is approximately a job. And the pet ad says, I'm a pet, I'm looking for a buyer, I want a dog lover. If you're not a dog lover, I will not even look at you. I don't care what kind of dog lover are you, as long as you're a dog lover. And here is my attributes, so you know what I am. And then a buyer comes in and say, I'm a buyer, and I'm looking for a pet. And what I need is that this pet is actually a dog. I can afford it. It's either large or very large. And if you can find me anything of this, if it is the Sam Bernard, I'll be really happy. And this is my account, and I'm a dog lover. And then you can imagine how the matchmaker compares the two and see, oh yeah, these two, the match made in heaven, let them work together. So this is an overview without any implementation. Now, let's go a little bit in the details of how actually this is implemented. So, Condor, it's of course just processes, it's ID. So you have different programs, different processes that run on a machine, and this is the list of essentially all the processes you have to care about in a Condor proposal. And I'll go over them one by one. Oh yeah, and here is another slide to see which processes run on which nodes. So essentially on your submit machine, you will have a master, a skd, some shadows, and a property. On an execute node, you will have a master, a start-d, and a starter, and finally user jobs. And on the central manager, you essentially have master, collector, and machine. So let's start with the Condor master, which is everywhere. And Condor master in the end does very little. It essentially starts everything else. It's a starting point for when you start a Condor daemon, you start a Condor master, and you delegate to it to do everything else. And the reason for doing this is twofold. One is, well, threefold maybe. One is it's easier, especially if you have to start more than one process. Two, if one of the processes is started exits, the master will restart it. The master is very small, so it's unlikely to crash. So by using a master to start a more complex process like a schedule, which is huge, if the schedule crashes for whatever reason, the master will restart it. So you don't have to do it by hand. And also, I'm not completely sure I like this behavior, but if binary is updated or a daemon is started, the master will restart it automatically. If you want it or not.
You can disable that.
You can that? Okay, good. Sometimes it's annoying. The master also provides access to remote administration. So you have a single point. You can use the same command for all the daemons, and the master will propagate the information to the others. Stuff like on config, start, off, on. And it is also the default server for many other commands like the Condor config val. Again, you send it to the master will spread to the others if needed. So it's just a nice starting point for everything else. Now the Condor property, you have it in the submit and execute node, and essentially what it does, it monitors the process tree of the other daemons and sees which processes start, which end, how much memory they use, how much CPU they use. It's very useful for the execute node because this is how the startd, which we'll talk in a second, gets the information about how much memory is used and how much disk is used and stuff like that. But it's useful also on the submit node for similar reasons, although not exactly the same. But those are just essentially help processes. Now we go to the meat of the Condor daemons who do the real job. And on the submit node, this is the Condor schedule. This Condor schedule represents the jobs in the Condor pool. The user submits to the schedule. The schedule takes hold of the job, keeps it, maintains it, and makes sure it comes to completion if possible. It maintains persistent queue of jobs, and it's not really a queue in the sense of first in, first out. There are priorities in the schedule. We'll talk about that in later talks, but just to make sure it's not really first in, first out. And another thing to understand is that each node that runs a schedule has its own queue. So the schedules don't talk to each other. They are completely independent. The schedule is also responsible for contacting the available machines and spawning the waiting jobs when told by the negotiator. Not on their own, but when the negotiator tells you have a machine, it's the schedule that goes to the machine and actually sends the job there. At least starts the communication. And it also services most of the user commands like Condor submit, Condor rm, Condor queue, Condor help, Condor release, and so on. Something that is very related to the schedule is the Condor shadow. And essentially, after the schedule contacted the machine, and makes sure that it has the claim, it starts a shadow and delegates all the further communication with the machine for that specific job to the shadow. And the shadow from that point on represents the running job, which means you have one shadow per running job. So you will have a lot of shadows on your submit node. It also handles file transfers, it enforces the various periodic star expressions like hold, release, remove, and so on. So while most of the time does very little, there are period bursts of activity when it's very active. And that's pretty much all we have on the submit node. So let's see what is on the execute node. And like we had the schedule on the submit node, the startd, it's what owns an execute node. It essentially represents a machine that is willing to run a job in the Condor pool. And enforces its wishes. So when the startd sends a class out that says, I require X, if for whatever reason a schedule comes to it and says, there is a job and that requirement is not met, it will turn it away. So it rechecks that what its own requirements, it's actually valid independently of what the negotiator did. So most of the time it's not a big deal because the negotiator will do the right thing. But if either things change between the match and the moment the schedule contacted it, or for whatever reason the negotiator misbehaves, the machine will actually enforce its policy. It will start, stop, and suspend jobs, and provides other administrative commands like Condor vacate, which essentially kicks the job off the node. And similarly to the submit node, there is another process that actually does the real job. After the schedD talks to the startD, the starter is started. So for each CPU, or actually each logical slot on the node, you have a Condor starter. And this is the one that actually gets the file, starts the job and manages the job, and then sends back the output of the job. And again, you will have one per running job, but usually you don't have that many slots, so it's much less of a concern than it is on the submit. But with the multi-CPU nodes these days, you get a few dozen pretty easily. Now, let's go to the central manager. You have the master, but one of the most important processes in the Condor pool actually runs here, and this is the Condor collector. This collects information from all the other daemons, and it's actually what defines the Condor pool. This is really what the Condor pool is all about, the Condor collector. The daemons will send periodic updates to the collector about every 5 minutes by default. And all class S will be removed after I time out. So if a daemon goes away and it doesn't update its class at in 15 minutes, it's like it never existed. The collector will get rid of it. This is nice, so you don't have old stuff in your collector. You always have fresh stuff, and anything that dies just goes away. There is a new thing called offline class adds that you can set that will actually store to disk old class adds. We will not discuss that. Just for your information if you want to research it later on. It services queries for information, queries from other Condor daemons, and also from the users. When you run Condor status, it goes to the Condor collector. The other process that runs on the central manager, it actually doesn't need to run on the same machine as the collector, but it typically does. It's convenience. Is the Condor negotiator, and this is what actually does the matchmaking. And a little more detail how it works. Essentially gets all the available machines and then contacts the various schedDs in certain order and gets their jobs, does the match, tells the schedDs until it exhausts all the available resources it has. It also handles the user priorities on account, which we'll not discuss too much in detail today, but this is where all the priorities are handled. This is the staple Condor pool represented in the Condor manual. I prefer this one, so I'll go to this one. So essentially, you have machines. Each machine has a master, a startD, and a shadow, and finally a job. A submit node has a master, a schedD, eventually a shadow when the job is matched. In the center manager is master, a collector, a negotiator, and I skip the prop_div because while it is there and doing useful thing, you never really interact with it, so you don't really care. So, a word about how you cross firewalls. So, by default, Condor wants to write two-way, essentially peer-to-peer communication. Everybody talks to everybody. Unfortunately, this was nice in the early days of the internet. These days, nobody really wants to work in this situation, or you really have to really force them to drop their firewalls. So something needs to be done to make it work. So in Condor, the answer is CCB, or Condor Connection Broker, which essentially reverses the connection. So you have to have the CCB on a public network, so on a firewall here, you can afford one. And since you will have few submit point and many execute node, we assume that this is on the public network, but this is all firewalls. And now, when a match is made, we said the schedD will try to talk to the execute node. But if this is behind the firewall, this will never work, right? So what CCP is here for is to reverse the connection from here. So what happens is the start D, when it starts up, it opens a permanent connection with the CCP and advertises in the collector, if you want to talk to me, talk clearly to the CCP, and CCP will relay your message. So when a SCED wants to talk to the start D, it essentially talks to the CCP and say, can you please tell the start D to call me back at this address? This is relayed over this existing connection to the start D, and the start D at this point calls back to the SCED D, opens a permanent TCP connection, and then that connection is used for all further communication. Or this is a rough approximation, but I hope this gives the idea how it works. And what are the limitations of CCP? Well, CCP must be accessible by everybody. And by the way, the collector itself acts as a CCP. And requires outgoing connectivity. And you cannot have both sides behind the firewall. So if both the execute machine and the submit machine are behind the firewall, it will never work. Because you cannot really call back, revert the connection, because you need one-way incoming connectivity, or it will not work.
So one is like in a DMZ, and the other one is behind that firewall with the firewall open, so it can communicate on those ports.
If you open the ports, that's fine. It doesn't. The demons don't know how your network topology is. But if you close completely all incoming connectivity, it will not work. Okay. If you open certain ports and tell it to use certain ports, it will work. Okay. Because from the common point of view, there is no firewall.
All right.
But yeah, if you cannot call in, you are just dead in the water.
You're just stuck.
Yeah. Okay. Oops. This was all for the high-level demonish description. And let me show you a few slides about how the matchmaking protocol or the name protocol actually works. So you start with an execute machine that is empty, and a submit the machine that actually have a job that needs to be matched. So start D will send its class at the collector, and the SCED told the collector before that I'm here if anybody asks about me. I'm not showing it. Now the collector will, the negotiator will ask the collector for all the class ads from jobs, from machines, get it here, and then get from SCED the jobs. If the two match, the match will be made here. Todd, what was that queue for? I couldn't remember. It was from your slide, so.
Yeah. What was that for? I'm not sure about the questions.
It's in two places.
It was for clearing?
I don't know.
It will come to me shortly.
Yeah. So the negotiator tells the SCED that it should talk to a specific start D. So the SCED contacts the start D, gives it the job, and start D again does the match, as we said. It will enforce its requirements. At this point, the central manager is out of the picture. The two of them are claimed to each other, and they will start a shadow and a starter. And at this point, the two actually talk to each other, and the job will be started. If a job finishes, the SCED through a shadow will start another job without going through the center collector. So essentially, once a claim is made between a start D, a SCED and a start D, it is long-lived. It is not for a single job. It can last hours, days. It's a configuration variable, but it's typically quite long. So essentially, jobs continue to be sent, jobs with the same characteristics, of course, because else this one will refuse it. As long as they have the same characteristics, jobs will continue to be sent to the start date as long as the claim is valid, and the negotiator will never know about it.
And for how long it is?
I think the default right now it's a day. It was a month, which was ridiculously long, but I think right now it's a day.
The default for how long a claim is?
Yeah,
I don't know that there is a default.
it is. There is one.
Max claim length?
I think there is a max data. That,
Oh, the
Max claim workload? I don't think. Claim workload? I don't think there is one.
no? I thought there was one, but okay. We can discuss this during the coffee break and dig down if you are really interested. I can tell you in the glidines it's forever, because the glidines go away in a while. So, when will the claim be released, which is pretty much along those lines. At least if the lease is not renewed, for example, if machine's powered on, the demon dies, everything is leased, it's temporary. If the machine goes down or anything like that, this is nice. For example, in the gliding world, the gliding disappears and the starter dies. You don't want the job to be linked to that starter forever. So after, I think the default is 20 minutes, and you notice, oh, the machine disappeared. I'll break the lease and I'll go to the negotiator to get a new one. The SCAD can break the lease. For example, I don't have any more jobs, so even if I have been given a lease forever, I ran all the jobs that match that specific job type, so I have nothing else to send you, so bye. The start date can actually break it. You reach the limit of the lifetime. It may prefer a different match via rank, which is quite dangerous. If this happens, your job is kicked off immediately. So using rank on the machine is actually very dangerous. Or, for example, if you are in an opportunistic way, like the desktop machines, somebody starts using the machine and you're kicked off. The negotiator can actually release a claim because there are priority issues. So somebody with higher priority is up and you have preemption enabled. The negotiator will tell the SCAD and the start date, break your own list. I really want you to change and give the lease to somebody else. Or you can do it explicitly with the Condor blockade command, which essentially says kick off the job you're running. And this is all I have for this talk.